In this first part, we used a circuit with a data selection IC known as a demultiplexer or demux. A demux is a combinational logic circuit that has one input and more than one output. It receives the information on a single input and transmits the same information over to one of many outputs one at a time. A demux is used when a circuit wishes to send a signal to one of many devices. Here we have the LEDs connected to the first 8 outputs on the demux. As you can see, we are using the 4 push buttons to turn on the LEDs in order, from the first one to the 8th. Here we switch the connection of the LEDs from the first 8 outputs to the 9th to the 16th outputs. And again we are using the push buttons to turn on the LEDs in order. In the truth table, 0 stands for the button not being pushed and 1 means the button is being pushed. In this part, we built a 7-segment display driven by a 5-5 timer and a 4-bit counter. R1 is the charge resistor and R2 is the discharge resistor. Current flows into the capacitor via R1 and R2 in series. The voltage on the capacitor rises. The 2 resistors and the capacitor between them set how long it takes the capacitor to fill, so they affect that part of the oscillator cycle. At a certain voltage level, the 555 decides there is enough voltage on the cap, so it turns on a discharge transistor inside it. The capacitor now discharges via R2. The cap and R2 set the time taken for the discharge part of the oscillator cycle, so the capacitor slows down the rate of rise and the rate of fall of voltage. Without the capacitor, the circuit would try to oscillate very fast and would not be controllable or predictable. The smaller the capacitance, the shorter between charge and discharge, meaning we have shorter time between the pulses. So the smaller the capacitor, the faster the count on the display. Here the push button is connected to pin 2. Each time the button is pushed, the number on the display freezes and the timer stops counting. Next we connect the push button to pin 15. Now each time we push the button, the number on the display turns to 0, so it resets. This happens because pin 2 disables the clock, so when the button is pushed, the clock stops working and stops counting. Pin 15 is the reset pin. So by pushing the button we are resetting the clock, which turns the number on display to 0. In part 3, we connected the circuit to a serial connection of the flip-flops and created a shift register. In a shift register, flip-flops take information from previous flip-flops, display the result, and then carry it on to the next flip-flop. We had some problems in this part. Even though we had the setup of the circuit right, we never got the right results. We had 2 teachers look over and check our circuit, and they couldn't find anything wrong. We tried replacing both of these 7474 ICs, but it didn't change anything. We also tried rearranging the setup of the circuit, but that didn't help either. Maybe the problem was that we were using a lot of wires and breadboards are very sensitive. But what we think is the most likely reason is that something must have been wrong with the connection in our breadboard. We think this because when moving this yellow wire from the VCC on the left side to the VCC on the right side, we got closer to the correct results. But this is the closest we could get to the right results, even with the help of our teachers. We were also told that we were not the only group that had issues with this exercise. In the first part, we pieced together a photoplethysmographier using infrared light and some other devices. Photoplethysmography, also known as PPG, is a simple optical technique which detects changes in the blood volume in the microvascular bed of tissue. PPG uses a low-intensity infrared light, and since light is more strongly absorbed by blood than surrounding tissues, the changes in blood flow can be detected by the PPG sensors as change in the intensity of light. The reason why light is more strongly absorbed by blood is because in the blood there is a protein called hemoglobin. But hemoglobin is very good at absorbing infrared light. AC component is one part of the resultant signal. AC component is attributable to the changes in the blood volume in the skin which is caused by the pulse. So the height of the AC component of the photoplasmogram is proportional to the pulse pressure. Now in this exercise we will build a circuit that filters infrared signal and employs AC component peak to light a LED. At first we built this circuit using a reflective optical sensor, resistors and a bipolar junction transistor, as can be seen in this photo. We could see that the circuit was correct and working because we saw the infrared light from the optical sensor through a camera phone. It was interesting to see that iPhone has an infrared light filter on the back camera but not on the front camera. So we could only see the infrared light through the front camera on our iPhones and Fabio's Samsung. Next step was to filter and amplify the V sensor output. At first we wanted to use passive high-pass filter and cut-off frequency of 0.7 Hz. We needed to calculate the resistor with the following equation. When active low-pass filter was used, we had to cut-off frequency of 2.34 Hz and signal gain of 101. We again needed to find the resistors R1 and R2 with following equations. Finally, the circuit was supposed to look like this. Now after the circuit was filtered, we needed to amplify the low signal once more, with another round of passive high-pass and active low-pass filtering, connected to the 5K potentiometer. The circuit was now ready to test the photoplethysmographier. Here we used our photoplethysmographier as replacement for the 555 timer. We then added a decade counter to keep track of our heartbeats, and we added the CO from one 4026 to another 4026 as its clock input. The second 4026 is connected to another 7-segment counter placed directly across from the first one. We added a push button to the reset pins on both 4026s so we could start over on our counts. First member was Sarah, and she had 19 beats for 15 seconds, so that is 76 beats per minute. The next record was Auntie's, and she had 20 beats for 15 seconds, so that is about 80 beats per minute. To make sure that the device is sensitive to changes in heart rate, we repeated the heart rate acquisition for the same members, but now we decided to hold our breaths for 45 seconds and then record the heart rate in beats per minute. We also took a record of the heart rate while we were holding our breaths. When we hold our breaths, we stop the oxygen flow to the blood. It will then take longer for the blood to fill the heart and thus also create a slower heart rate, which means that the heart rate decreases. Sarah was first, and her heart rate was 29 beats for 15 seconds, so that's 116 beats per minute after she held her breath. The record of Sarah while she was holding her breath was 90 beats for 15 seconds, While she was holding her breath, she started to feel the heartbeat more and felt like it was increased, but it did not. It was the same as the normal beat was. Next record was Artie's, and she had 30 beats for 15 seconds, so that's about 120 beats per minute after she held her breath. The record of Artie's while she was holding her breath was 13 beats for 15 seconds. For Artie's, she felt that while she was holding in her breath, it relaxed her, which can explain why hers is less than Sarah's.